Let's summarize the equations that we introduced in Chapter 2 of our study of basic thermodynamics. We introduced the concept of mechanical energy in a system, particularly kinetic and potential energy, where delta KE, which is the change in kinetic energy of a system during a process, it's just the kinetic energy at the end of the process minus the kinetic energy at the beginning of the process. And that is equal to 1/2 times the mass times the final velocity squared minus the initial velocity squared. Likewise, the change in potential energy during a process is just the potential energy at the end state minus the potential energy of the initial state. And that is equal to mass times the acceleration of gravity times Z2 minus Z1, where Z2 is the elevation above some data at the end state and Z1 is elevation above the same datum at the beginning state. We introduced the first law of thermodynamics for a closed system, and we just said that the change in energy during a process is the change in internal energy plus the change in kinetic energy plus the change in potential energy, and that is equal to Q minus W. Now, for many closed systems, in fact, most closed systems, we can ignore changes in kinetic and potential energy as being zero or insignificant. And the first law of thermodynamics, the law of energy conversion for a closed system, most notably is that the change in internal energy of a system during a process is simply equal to Q minus W. Now, we can write the same energy balance as a rate balance. And for a system operating at steady state conditions, we can say that the EDT is zero because it's operating at steady state. And that's just equal to Q dot minus W dot, where Q dot is just Q divided by time and W dot is just work divided by time. We also introduced the concept of work due to the expansion of a piston cylinder and other devices that produce work. It's just the integral from V1 to V2, those are volumes, times P dV. And we also introduced a particular type of thermodynamic process called a polytropic process. And this works for gases only. You cannot have a phase change during a polytropic process. And the equation describing the polytropic process is just pressure times volume to the n power is constant. And we can also use specific volume here instead of volume. It works either way. So if n is not equal to 1, we've integrated this work equation, and we get that work for a process from state 1 to state 2 is simply P2V2 minus P1V1 over 1 minus n. Now, if n is equal to 1, the integral solution is different. The work between states 1 and 2 is just P1V1 times the natural log of V2 over V1. And in the particular case where we have a constant pressure process where n equals 0, well, that would be this first equation here because 0 is not equal to 1. If we put 0 in here and make the pressures constant, we find that the work done in a constant pressure process is simply the pressure times the change in volume. We looked at heat transfer, conduction. The rate of energy transfer is simply the thermal conductivity of the material we're conducting heat through times the area divided by the length, or let's call it thickness, the dimension and the direction of heat flow, times the difference between the hot temperature and the cold temperature. With convection, we said the rate of heat transfer is the convective heat transfer coefficient, which are largely empirically defined, times the area over which the heat transfer takes place, times the difference between the hot and the cold temperature. Now, for radiant heat transfer, we actually had two equations. If we looked at simply the amount of radiant energy, that is equal to the emissivity of the material, which is 1 or less, times the Stefan-Boltzmann constant, which is just that, it's a constant, times the area from which the energy is radiating, times the absolute temperature to the fourth power. Now for net radiation emitted, this is where we're emitting radiant energy according to this first equation, but something out there is radiating back, and that we'll regard that as T sub C. And so the net radiation emitted is what we send out minus what we get back. And that's just going to be the emissivity times the Stefan-Boltzmann constant times the area radiating energy times the hot temperature minus the cold temperature, each taken to the fourth power. We introduced power cycles, and we did a simple energy balance on a power cycle, treating it as a closed system. And what we found was that the work done by the cycle is just QH minus QC, where QH is the amount of energy transferred into our cycle by a hot reservoir, and QC is the amount of energy transferred from the system to a cold reservoir. And the efficiency of a power cycle, which is a number of less than 1, it's simply what we want divided by what it costs us to get it. What we want is the work output, and what it costs us is the heat input. So using the energy balance substitution, we get that the efficiency is QH minus QC over QH, which we can simplify to 1 minus QC over QH. Now we also took a quick look at refrigeration cycles and heat pump cycles. And interestingly enough, the energy balance for refrigeration or heat pump cycles gives us exactly the same equation as we got for a power cycle energy balance. And that is the work of the cycle is just QH minus QC. Now for a refrigeration cycle, we don't have efficiency, we have a coefficient of performance. We'll call it beta. And the beta is simply what we want divided by what it costs us to get it. And in a refrigeration cycle, we're interested in keeping the cold side cold. So what we want is this heat transfer term QC. What it costs us to get it is the work that we have to put into the refrigeration cycle. And we can rewrite this as QC over QH minus QC. Now a heat pump also is rated by a coefficient of performance. We'll call it gamma. And again, it's what we want divided by what it costs us to get it. Well, with a heat pump, we want to keep the warm side warm. So we're interested in QH, not QC. But what it costs us is the work that we put in. So the coefficient of performance for a heat pump is simply QH over QH minus QC.